Assalamualaikum and a very good day. We are from Group A and today we are going to present a topic about triple integral in cylindrical coordinates using divergence theorem. I am BALQIS binti ROSLI and these are my group members. Muhammad AKMAL bin Abdul Aziz, Muhammad IZZUL IFKAR bin SAIFUL, SUKAIRI and AMAR SAUFI bin NASIR. I will explain about the introduction of triple integral of cylindrical coordinates. In 3 dimensions, there is a coordinate system called cylindrical coordinates. It is similar to polar coordinates and it gives a convenient description of commonly occurring surfaces and solids. As we will see, some triple integrals are much easier to evaluate in cylindrical coordinates. In the cylindrical coordinate system, a point P in 3D space is represented by the ordered triple R, theta and Z, where we can see based on the figure, R and theta are polar coordinates of the projection of P onto the xy plane, while Z is the directed distance from the xy plane to P. To convert from cylindrical to rectangular coordinates, we use x is equal to r cos theta, y is equal to r sin theta, and z is equal to z. To convert from rectangular to cylindrical coordinates, we use r square is equal to x square plus y square, tan theta is equal to y over x, and z is equal to z.
Divergence theorem. It is also known as Gauss theorem. Evaluate surface integrals directly can be tedious, particularly when we have the outward unit normal changing at each point on the surface. So we need to break the surface into several subsurfaces according to their orientation. Gauss theorem establishes a relationship between a surface integral over the boundary of a solid and a triple integral over the solid. It is in effect a generalization of the normal form of ring theorem in 3 space. Suppose G is bounded by a closed surface S and N is a unit normal vector outward from G. If fxyz is equal to fxyz I plus gxyzj plus hxyz zk is a vector field which fxyz, gxyz, hxyz have continuous partial derivative in G, then S double integral f dot m ds is equal to G triple integral delta dot f dv, where delta dot f sometimes written as divergent f is equal to delta f divided by delta x plus delta g divide delta y plus delta h divide delta z.
For the question, assume that the water tank has a paraboloid shaped roof. Let Q be the solid bounded by the paraboloid. Z equal to 2 minus x power of 2 minus y power of 2. X power of 2 plus y power of 2 equal to 1 and z equal to 0. Applying the divergence theorem, find the flux of the vector field f x y z equal to x power of 3, y power of 3, z power of 3. Flux is a measure of the number of field lines that pass through a boundary. Typically, we compute flux using a surface integral. However, when we have a closed surface and a field that is defined everywhere inside of enclosed region, we can take advantage of the divergence theorem, which is allow us to change closed surface integral into volume integral instead. In general, we write this equation. Also, we will find it convenient to use cylindrical coordinate.
For the calculation, first find the divergence of the vector field. Given the vector field fxyz equal to s power of 3, y power of 3 and z power of 3. Using the formula there, we can get del dot f equal to d per ds s power of 3 plus d per dy y power of 3 plus d per dz z power of 3, and then we can get 3s squared plus 3y squared plus 3z squared. After that, we can convert the equation to the cylindrical coordinate, which is s squared plus y squared equal to r squared and z equal to z. Then we get 3r squared plus 3z squared. Now we are bound in between the surface of the z equal to 0 cylinder and the given paraboloid. From the figure, region G is the solid and the region R is the projection on the SY plane. From this figure, we can find the limit of Z, R and theta. For the limit of Z, we get 0 to 2 minus x squared minus y squared. Then we convert to the cylindrical coordinate, we get 0 to 2 minus r squared. For the radius r, we get 0 to 1. For the theta, we get 0 to 2 pi. After we get the limit, we can now use the divergence theorem to find the flux of the field across the bounded paraboloid and cylinder. Given that flux equal to integrate f dot ds equal to triple integrate del dot f dv. We know that the dv is for the cylindrical coordinate dz r dr d theta.
First, we put the value of the divergence of the f, which is 3r squared plus 3z squared, into the triple integral formula of solid. So the equation will be triple integral 3r squared plus 3z squared dz r dr d theta, which limit for z is 0 to 2 minus r squared, and limit for the r 0 to 1, and limit for the theta 0 to 2 pi. First, we integrate the equation with respect to dz with limit 0 to 2 minus r squared. Then we get c r squared minus 3 r power 4 plus 2 minus r squared power of 3. Then we integrate the equation respect to r dr. Then we multiply the r into the equation. Then we get c r power of 3 minus 3 r power of 5 plus r 2 r multiply 2 minus r squared power of 3. Then we integrate that with limit 0 to 1, we get 23 per x. Then we integrate the equation into the respect to d theta with limit 0 to 2 pi. Then we get 23 per 4 pi is equal to 18. So the final answer is 18. So the flux of the field across the water tank is 18.
And now we are using the GeoGebra application to plot the solid with the equation given. Then we are using the photomat application to prove our calculation. Thank you.